Excellent. We're going live. Good afternoon, and welcome to MAE 113, Calculus for the Liberal Arts. My name is Richard Gohar, and this is Lecture 20. And this is part 2 of our optimization discussion. And again, thank you for tuning in. Make sure that you say something in the chat. Make sure that the audio is working this time. And, oh, excellent. Good. The audio is working. You can all hear me. Excellent. Thank you. So, right. We're going to do in today's lecture optimization. We're doing some more problems. So, I guess I'll start out with this example. Yeah, and the emojis are good too. Keeps everything in check. So what I'm going to say is, what I'm going to do is I'm going to explain it to you just a little bit. So, for instance, I'm going to have some sort of piece of card, and the idea is that that I should be able to, let's say, roughly like this. I'm going to cut out squares like this. And then some scissors. Some really old scissors, but they still work. Cut out the little squares. Trying to keep that neat. Yes, you will be able to see your quiz marks. There's that setting that I have to uncheck or something. Yeah, I'll try to fix that after. As you can see, I'm right in the middle of a nice fine arts and crafts project here. Slowly cutting out some squares, but yes, you will get to see the results. All right. Why am I cutting out? Okay, so I got 4 identical squares. And the idea is that from this piece of cardboard, or card that I have right here, so I have these 4 squares. The idea is that I should be able to fold up the little, oops. My vocation was not in box making. My vocation was in math. So if this box does not work out very well, we'll say that this is for illustrative purposes. So, so the idea is that it forms a nice little box, and it shouldn't have any gaps, of course, but like there should be equal. And if I had done that properly. So the idea is that I have, a nice little open box. I don't have a little cap for it, but this is the idea. So what the example is that here's kind of like the criteria. I have a piece of cardboard. Okay, and we're going to say that it's 16 centimeters by 10 centimeters. So this is, we'll say that it's like this. Yeah. So that's kind of the idea. So I have that. So I'm going to draw just a little symbol here. Maybe I'll just draw it like here. So I have a little cardboard here, and the idea is I'm going to cut out identical tabs here, identical tabs here, and identical right here. Perfect. And I already know we're going to say that the long side, this is 16 centimeters. on this side here. Oops. This is 10 centimeters. And then we got to figure out what the question they want is. What dimensions of the box yields the maximum volume? Okay, so we have this kind of thing, and then the other one is we'll have some sort of box. So I'll try to, you know, just kind of looking at like that. So it kind of, we're going to draw a 3D. So it's 2, there we go, something like that. Okay. So what we need to do is we need to introduce some notation into this, because the dimensions of this depends on what these squares are that I cut out. And in geometry, we used to mark off, you know, things that were equivalent length with something like that and something like this. So these are equal. And so what we're going to do is I'm going to put this as x. So I'll flip this over so that when I do flip it, this is x, and here's x, here's x, here's another x. And I'll copy this on here as well. Okay. So that when I do flip this up, I can already start to figure out what the height of this box should be. And this height should be x. So right here is x. Now, this is where we need to figure out what the other lengths and width are here. So for this length right here, so when I do fold this up, I'm trying to figure out what this length is here, or this right here. And to do that, I'll fold this down, and I know that this length right here, the total length from this that we had cut out was 10, and then we have 2 of these here that we're cutting out. So this length right here, or right here, is 10 minus 2x. So same thing here. This length here is 10 minus 2x. So when I fold this up, I can see this. Oops, and of course I smudged it. There we go. That this length here is 10 minus 2x. So again, 10 minus 2x. And what's the next thing? Well, we got this one little part here too, this flappy bit, and same idea. This entire length here is going to be 16, but I'm going to subtract off the 2 x's. So that should give me this length right here. So that's 16 minus 2x. So same idea here. This length here is 16 minus 2x. And when I fold it up, I know what this long part is right here. So that's 16 minus 2x. Okay. So I've already started to introduce some variables here. I don't know what the x is. So what I should actually do is start to define my variables. So I'm going to define my variables. So I can call this maybe my first step. And I'm going to let x is the length of one side of the identical square or squares. I don't want to have a minus. I'm going to just make it a box. There we go. So what's the next one? I'm trying to not use symbols that people using a dash could be a negative sign, so I don't want that. Then the other one, I'm going to say that I'm going to use V for volume. So V is the volume of the box. Okay. So then the second thing is for those that have done optimization before, we have something that we have a function. So there's a function that we'll need to maximize. Or this is the time now where we can actually introduce, this is the objective function. So this is the function that we're going to be manipulating to maximize or minimize. So we need to, let's say, oh yeah, well, what's the volume? What's the volume of a box? So volume. So when you do a volume, like when we think of this, like if this is going to hold water, it's liters cubed. And the reason for that is because we're doing length, so it's this, times the width, times the height. So we have H. So for the volume then, so this is what we're kind of thinking. So we're going to write a function, so we'll call it v of x, because what I'm going to do is I'm going to do the length, so here's the length, which is 16 minus 2x, times the width, which is 10 minus 2x, times x. So there's my length, there's my width, and here's my height. Okay. So what we can do is we can actually expand this out. And let's see, how do I want to approach? So you can do it any way that you want. I think what I'll do is I'll do just as it is right here. So I got 160 minus 32x minus 20x plus 4x. And Mr. MAE, please keep an eye on my signs, please. And that's the end of that. Hopefully I did everything correctly. I foiled this out, or foiled, it's that distributive thing that I'm doing right here. So here is right here, and use my other colors. There we go. No one saw that. There's supposed to be a square there. And next. We're almost done. Minus 48x. Did I do something? Somebody better correct it. Oh, okay. I was a bit worried. Hopefully, no, just being okay. Okay, good. Excellent. So what I'm gonna do, I got this. Okay, perfect. So I'm gonna just expand that out. Oops, that was the sound of the scissors. And okay, I think the other thing, what I'm going to do is, I know, I'll pull out a 4. 4 goes into 52 13 times. 4 goes into, okay, yeah, 160, or 4 goes into 16 4 times, so that's 4, or because of the 0, it's 40. Okay, so we have our objective function. The next one is, what is our interval? And for those that we know so far, what we're going to do is we're doing really what is called a mathematical optimization problem. So if you're in the upper year classes, this is called mathematical programming. And programming is an old term, not like coding in terms of like a computer code. This comes from the 40s, and it was by a man named Danzig who came up with programming. And programming means planning. So this was before the days of computers. And so what we're going to do is we're going to be doing something of, we're going to be maximizing the volume. So we're maxing the volume of X. And we need some constraint. So subject to, or such that, depending on who you talk to. The interval is our constraint. So what do we have for a constraint? Okay, 160. Yes. Perfect. Thank you. I have to remember to look up at the screen. Yes, thank you. Okay, so for the interval, what are some things that we need to make sure? First of all, this is a length. So like X, like this little square here, the smallest it can be is 0. Then it's just back to the card, right? And that volume would be 0. Yeah, we can factor out another X. But hold tight for that. There's a reason for why I'm going to do that. Partly just for the math side of things. We'll get to that. Okay, so for the interval, we're going to say that X has to be greater than 0. The other thing is that this side has to be can't be less than 0. So again, I'm going to say that the side, which is 16 minus 2x, has to be greater than 0. So that's what I was having up here. So this has to be greater than 0. And the other one is that we have 10 minus 2x is greater than or equal to 0. Okay. So this is fine. I'm going to do a couple of steps here. So I'm going to solve for x. So 16, and then the 2x comes over to the right-hand side. Divided through by 2 on both sides, I get 8, which has to, so x has to be less, x has to be less than 8, or less than or equal to 8. And then same thing over on this side. I have 10 has to be less than 2x. So that implies that that x has to be less than 5. So from these, I know that x has to be greater than 0. And to satisfy all these conditions, x has to be less than 5 as well. Why can x equal 0? Well, it's possible. It is allowed if I let this be 0. But basically then I have, if I do that, then this is 0, which means then that this whole volume is 0. So it's not going to be a good solution, but it is allowed. So I mean, if you really wanted to, you could make this greater than 0 if you wanted to eliminate that. But for this case, we're going to include it. And the reason for that is because we're used to working on a closed interval, right? We need that closed interval to use the closed interval theorem that we had from our previous lecture. So yes, we need a closed interval. It's good that you're telling me, yep, I'm good, because I'll just keep talking until somebody tells me to stop. Then, so again, that means that x is an element from 0 to 5. So we can say that, some people could write it like this, which is so this is kind of one form to write it if you're getting up into higher classes. The second year class might do something like that, or you might see something like this, which is just max of v, and under here is the condition, x is on that closed interval from 0 to 5. So there's kind of like two different standard notations. Okay, so we have a closed interval. Now we can actually start to apply our optimization technique, which is so this is where we apply our optimization technique. So we have this function, and it's cubic. So it should look something, it's cubic, and it's positive, so it should look something like this. And we're going to be on some sort of closed interval from 0 to 5. Again, I don't know where the bends are in it yet, but the idea is that we want to find where, like for instance, I think something like this, it could look something like that. So again, from 0 to 5. So we can be looking for something where these points, we're looking for the minimums and maximums. So those occur, the candidates, for where these could occur is where the derivative is equal to 0. So that's what we'll need. We need the derivative. We're not using f, we're going to use a v. Take that derivative. So using our constant multiple rule, I'm going to just write 4 in the front here and take the derivative of the inside here. So I have 3x squared minus, then I have 26x and plus 40x Everyone's okay so far with this? And then what I can do now is I'm going to factor this out. Okay, so there's my factorization. And again, if you multiply that out, I get my 3x squared. I have minus 6 minus 20, so that gives me the minus 26. And then the minus 20 times minus 2 gives me the plus 40. So we need to, this is the part B, we're set this derivative equal to 0. So to do that, this means that 3x minus 20 equals 0, or 23x, and I get 20 over 3x. Similarly, I get x minus 2 equals 0, or x minus 2 equals 0, then that means x equals 2. So here are my two critical points, or critical numbers. But again, referring back to our interval, we're working on the interval 0 to 5. So this is okay. 2 is in 0 to 5. But for those that might not know about, let's say 20 over 3, that's approximately 6.67. So again, that is not in the interval from 0 to 5. So I don't have to worry about this one. So this one is not admissible. So now we can go to C. I'm going to make a table of values. Oops. There we go. So here's x. Here is my v of x. Now again, this is the original function. I want the values of the original function, not the derivative, because the derivative is telling me where to look in the original function. So I know where to look now, and I know that my interval is from 0 to 5, so those are my two endpoints. And I also have a critical value to investigate, which is 2. So putting that back into the original function, I got 0, so that one's easy. 0 times this gives me still 0. That was easy. I can do 5 for you. That's also very easy, because if I put in 10 minus 2 times 5, that gives me 0. So I can just write that here. 16 minus 2 times, 16 minus 2 times 5 times 10 minus 2 times 5 times 5 again. So I got 10 minus 10, that equals 0, so this equals 0. And this is where the harder part is, where I have to actually do some arithmetic. Times 2 times 2. So I get 16 minus 4, 10 minus 4 times 2. That's 12. This is 6, and here's times 2. So 6 times 2, that's 12. Times 12. 12 times 12, or 12 squared, is 144. Okay, so again, this is where we look at the The biggest value here is 144. So this is our global max. It's our global max because we're on a closed interval. And then what else can we do? Oh yes, a very big step in business or economics. State your conclusion. So, again, the conclusion is probably an answer to your original question or hypothesis, and it's, what's the dimensions of the box that yields the maximum volume? So I can tell you that the maximum volume is 144 centimeters cubed with dimensions and then I can actually, I have it here, I can read them off. 12 centimeters by 6 centimeters by 2 centimeters. Oops. And that's it. So we're done that question. So that's the end of that one. So what we should do is we should summarize. Let's summarize. What did I do? Well, the first thing was we need to understand the problem. Again, you should, you should be asking yourself questions like, what is unknown? What's known? What's given? What are some conditions? It sounds like we're making a box to ship wallets in. Sure, yeah, we could put sometimes, yeah, a banker's box. It's amazing that people spend so much time on the packaging now due to the popularity of unboxing videos online. Some of the boxes that I've, the latest electronic products that I've received some of the boxes are beautifully packaged now. So, customers may be wanting that. Draw a diagram. If you're not super great with seeing this in your head, pull out even something that's physical and tactile. You can actually sit there and work that out and fold up the box and come up with your dimensions. So drawing a diagram is important. Then what I started doing next with this orange bit here, I started introducing some notation. I started defining my variables. Defining variables. You could also be thinking this. I also kind of think of defining variables or something like that as part of understanding the problem. These are kind of cyclic. You can kind of go through all these. So we've introduced notation. And then apply optimization techniques. And after that, I think the fifth step is also quite important, which is State your conclusions. And then here's another thing that most math people won't put in a textbook. Check, either using a different method, or does this make sense? So when you get to the end, when you state your conclusion, hopefully as you're saying this out loud to yourself, that, for instance, we messed up and you missed, say, finding this step right here. Let's say, for instance, I'm just going to cover this up. There we go. Cut that off and say, I didn't get that one solution. I only got 0 and 5. At the end, when you're going to say to your boss, we're going to maximize the volume by doing absolutely nothing to the card, by saying x is equal to 0. That doesn't make sense. And again, it doesn't solve the problem of we need a box, and this is just a piece of paper. So little checks like that can help. Again, does it make sense? I wish people asked that question more often. If the X was bigger than the length or the side of the cardboard box, that would also be a problem. Okay, so we've done something that's kind of illustrating a standard technique, which is kind of basic problem solving. You know, write out your knowns, your unknowns, start to introduce some variables, introduce a diagram. So here's another example. So we have say Bell is laying a cable. They're laying a fiber optic cable. And if you want military application, say that this is out now in a field. We're setting up base communications between two things. So they have two new subdivisions that they're trying to lay some cable for, and they have two subdivisions. Are located on opposite sides of a creek that's 100 meters wide. Okay. And then they have that the bell has to connect between 2 points so along a bank of the creek. Where 1 point on the north bank is 120 meters east of the point on the south bank. Okay. Here's some more information. They say that it costs $40 per meter for underground cable, and it costs $80 per meter for underwater. And then they go, what is the cheapest way to do this? So that's it. So you'll probably get like an email or something like this. And at that point, you'd wish somebody should have opened up Paint and they should have drawn me a diagram or something, right? Yeah, and that's just not how it is in the real world. It would be nice. But that's why they're paying you. They go, here's all this information, now go figure it out. Okay, so what I'm going to do is I'm going to start to do a little drawing. Yeah, so I have some, what I'm going to do is I have a bank or some sort of river, creek. No, we called it a creek. Okay, so there's two subdivisions, some subdivision over here, some subdivision over here. And they told us that along the bank of the creek we're one point on the north bank. So let's say that this is the north. Here's the south. 1 point on the north bank, so we'll say up here, is 120 meters east of the point on the south bank. So, okay. So it's not over here, it's over here, because this point is going to be 1,200 meters east. This point here. I don't even know what a Starlink is. If it's wireless, in terms of for military applications, they like to lay down cable again because Wi-Fi is susceptible for man-in-the-middle attack, I think is the. So here's some subdivision. Again, we're paid to think and diagram. I'm not paid for my artistic. Okay, so we know that this is supposed to be. Okay, so again, here's the information. This is good. So I've encoded this. I'm going to put this right here. Second. There's my right arrow. And so here, this is going to be 1,200 meters. And over here, we know that this is opposite of a creek, that it's 100 meters. So here's 100. Oh, high-speed satellite internet. Ah, okay. Yes, I think I remember I've tried high-speed satellite internet when I was in the United States, and it worked fine when the weather was fine. Because it was a clear night. But if any clouds, yeah, the reception wasn't super great then. So here's my water, and okay, so I think I've done this. The other thing I need to remember is that it's $40 to lay cable underground, and it costs me $80 to go underwater. So what I need to do, so the idea is Pick a pen that, we'll call this point S. So the idea is I need to lay some cable here, and then go across the water somehow in a straight triangle, like, sorry, the hypotenuse of a right angle triangle. And again, we start to do the same idea. Now that we've kind of got our diagram, I got P, Q, and S is going to be my midpoint that I'm going to kind of not break, but like I switch from going from underground to underwater. And here, let's introduce our variable. So we're going to say that x is the length of underground and over here. So I'll put that as x, which means that this remaining part right here should be 1200, because I have the entire length is 1200 minus x. And right here, this is the one of the legs of the right triangle, and that's 100. And along here is the hypotenuse, and that will be kind of our c squared. So that length here, again, it's a, so here's my squared plus 100 squared. And then to find that length, it's the square root. Right? Because I have a, b, c. C squared equals a squared plus b squared, or c is equal to a squared plus b squared. That's Pythagoras. Okay, so the second part. So I've kind of drawn my diagram. I've defined my variable. What's my objective function? Well, from this, they want the cheapest way. That's code for minimum cost. So what we need to do is we need to minimize a cost function. So the cost function is going to be, this is the underground, so that's going to be 40 times x plus, and then it's $80 to go underground, which is this part right here. So that's 1200 minus x squared plus 100. Okay. Three. We need our interval or a constraint. So for this, the smallest that x could be is 0. And I could run the cable all the way to the end here, and that still doesn't do me anything. So like I could have 0 where it's just completely across, or oh no, I want to have it all across. So these are the two extremes that I have. So it has to be somewhere minimized over that. Now this is where we have to do we have to find the derivative. We apply the minimization technique, which requires me to find where the derivative is equal to 0. But we will have to continue that on Monday. That's all the time that we have for today's lecture. We'll pick that up on Monday. If you have questions, again, feel free to send me an email through my RMC account. I'll release the quizzes marks today. And of course, we have office hours beginning at 1, going to 3. If you have questions, feel free to drop by through the Moodle website. All right, have a great lunch, everyone, and I'll see you on Monday.